There is a rule in the universe that seems unbreakable. Things need time to grow. A star needs millions of years to collapse into being. A galaxy needs billions of years to build its shape. And a black hole, no matter how hungry it is, can only eat so fast. There's a speed limit on cosmic gluttony, and it means even the greediest black hole in existence should need billions of years to become truly monstrous. So when astronomers pointed a telescope at the edge of the observable universe and found a black hole already weighing billions of times the mass of our sun, sitting there before galaxies had even finished forming, they had a problem. This thing shouldn't exist. Not yet. Not this big. Not this early. And yet, there it was. Let's find out how something broke the universe's own rules, and what it means if the rulebook was wrong all along. How a black hole is supposed to grow up.
To understand why this object is so disturbing, you first need to understand how black holes are born and how they grow. Because normally, it's a slow and humble process, built one careful bite at a time. Most stellar black holes start small, the collapsed core of a dead star, maybe 10 to 100 times the mass of our sun. A cosmic seed, not yet a monster. Nothing about its birth is dramatic on a cosmic timescale. A massive star burns through its fuel, can no longer hold itself up against its own gravity, and collapses inward into a point where the normal rules of space stop applying. From there, a black hole grows the only way it can, by eating. Gas, dust, unlucky stars, anything that strays too close gets pulled into a swirling, superheated disk and slowly fed across the event horizon, the point of no return. But here's the catch. Eating too fast destroys your own dinner table. As matter falls in, it heats up violently, radiating enormous amounts of light and pressure, sometimes outshining every star in its host galaxy combined. Push too much matter in too quickly, and that radiation blasts the incoming gas away before it can fall in. It's like trying to shove food into your mouth so fast that you blow it back out with your own breath.
This creates a natural speed limit. One physicist actually gave a name, the Eddington limit, named after the astronomer who first worked out the balance between the inward pull of gravity and the outward push of light. Every object with enough gravity to hold on to material has a version of this limit. Stars have one, black holes have one. Cross it, and the outgoing radiation pressure simply overpowers gravity, and material gets shoved away instead of swallowed. Feed a black hole at exactly this maximum sustainable rate, and its mass roughly doubles every 30 to 50 million years. Sounds fast? It's not, cosmically speaking. Run the math forward from a 100 solar mass seed, growing at the absolute fastest sustainable rate, and it still takes over 700 million years to reach a billion solar masses. That's assuming perfect conditions the entire time. Constant fuel, no interruptions, no wasted centuries drifting through empty space with nothing nearby to eat.
700 million years is a blink in the 13.8 billion year life of the universe. But it's not zero. And that number is about to become a very inconvenient problem. In 2023, astronomers using the James Webb Space Telescope peered back at a galaxy so distant that its light left home just 470 million years after the Big Bang. 470 million years! Less time than our speed limit math needs just to build 1 billion solar mass monster from a modest seed. At the center of that galaxy sat a black hole with a mass roughly equal to the entire mass of stars in its host galaxy combined. For comparison, the black hole at the center of our Milky Way is a rounding error, less than 1/10 of 1% of our galaxy's total stellar mass. This new object
was thousands of times more dominant relative to its home than anything we'd ever seen. Imagine a toddler that somehow weighs as much as its entire family combined.
And it wasn't alone. Since then, JWST has kept finding more of them. Black holes with masses in the hundreds of millions to billions of suns, all sitting inside galaxies that are barely old enough to have finished forming their first generations of stars. Some are so bright and so early that earlier telescopes simply couldn't see them at all. They were invisible until we built an eye sensitive enough to catch their faint, ancient light. Using the normal rules, the Eddington limit, the slow, patient buildup from a stellar mass seed, there simply wasn't enough time. The universe was too young. The math doesn't add up. It's like finding a fully grown oak tree in a forest that was planted last week, or finding a fully grown adult standing next to a newborn's crib, claiming to be their sibling. To be fair, not every ancient black hole discovered so far is impossible to explain. Plenty of them fit comfortably inside the normal timeline if you're generous with the assumptions. But a growing handful don't fit no matter how generous you are. Some of them appear to be overweight even for the most extreme heavy seed maximum feeding rate scenario physicists can construct. Those are the true outliers, the guests nobody remembers inviting. So either these black holes cheated, or they never started small in the first place. Scientists have a few live theories, and none of them are fully settled, which is exactly what makes this such a good mystery. Nobody actually knows the answer yet. The first idea is heavy seeds. Instead of starting from the collapsed core of a single star, maybe the earliest black holes formed directly from the collapse of a giant primordial cloud of gas, skipping the star stage entirely and starting life already tens of thousands of times the mass of the sun. Give a seed like that a massive head start, and the timeline suddenly works without needing to break any speed limits at all. The hard part is explaining how such a huge, unstable cloud could collapse directly into a single object, instead of fragmenting into thousands of ordinary stars, the way gas clouds normally behave. The second idea is cheating the speed limit itself. The Eddington limit assumes a nice, tidy, spherical flow of gas falling evenly onto the black hole from all directions at once. But the early universe was chaotic, gas-rich, and messy. Some models suggest black holes could briefly gorge themselves at many times the theoretical maximum rate, using thick, lopsided disks that let radiation escape out the sides instead of blocking the incoming food. A short, violent binge instead of a slow, steady meal, breaking the rule not by ignoring physics, but by exploiting a loophole in the geometry. The third idea is that black holes didn't grow alone. Early galaxies were smashing into each other constantly, far more often than they do today, in a young, dense, crowded universe. Merge two mid-sized black holes together, and you instantly get a bigger one for free, no eating required. Do that dozens of times in rapid succession, hierarchically, black hole colliding with black hole colliding with black hole, and you can build something enormous without ever breaking the feeding limit at all.
The fourth idea is the strangest one: primordial black holes. Instead of forming from stars or gas clouds after the Big Bang, maybe some black holes formed during the Big Bang itself, born from tiny fluctuations in the density of the infant universe less than a second after it began. If a few of these ancient seeds were already enormous before the first stars had even switched on, they'd have a head start measured not in millions of years, but in almost the entire age of the universe itself. The honest answer is that it's probably some combination of these: a head start, a growth spurt, a series of lucky collisions, and maybe a pinch of primordial weirdness, all stacked together in the chaos of the infant universe. But even combined, some of these newly discovered black holes push right up against the edge of what any of these models can comfortably explain, and a few seem to blow past all of them at once. This isn't just a curiosity about one weird object tucked away in a corner of the sky. It's a crack in a model we thought we understood.
Our picture of how galaxies and their central black holes grow together, feeding off each other, shaping each other, regulating each other's growth over billions of years, was built assuming we had the timeline roughly right. Black holes were supposed to be the patient younger sibling, catching up to their galaxy slowly over cosmic time.
If black holes can get this big this fast, it might mean galaxy formation itself moved faster and more violently in the early universe than our simulations assumed. It might mean the seeds of structure were planted earlier and heavier than we thought, before the universe had even finished cooling from its birth. Or it might mean there's a growth mechanism we haven't discovered yet, hiding in the first few 100 million years of cosmic history, an era we've only just gained the technology to actually see. That's the uncomfortable, thrilling part. We're not talking about a gap in a textbook that will get quietly patched with a footnote. We're talking about a live, unresolved question being fought over in real papers using real data right now, because the telescope capable of finding these objects has only existed for a few years. Every time JWST looks a little further back, it seems to find another one of these impossible guests, arriving early, already massive, already breaking the rules we thought were unbreakable. Each new discovery either forces one of the four theories to bend further, or hints that the real answer is something nobody has proposed yet. And that's genuinely rare in modern astrophysics. Most mysteries these days are mysteries of precision, sharpening a number, tightening an error bar. This one is a mystery of principle. Something in our basic story of how the universe built its first giants is either incomplete or wrong. There's also a strange kind of comfort hiding in all this uncertainty. For most of the history of science, the universe has had a habit of humbling people who thought they had it figured out. Newton thought gravity was the final word, until Einstein showed it was really the bending of space itself. Astronomers thought the Milky Way was the entire universe, until they realized it was one galaxy among hundreds of billions. Every time we build a better eye to look further back in time, we tend to find something that doesn't fit neatly into the box we built for it. These impossible black holes might be the next entry on that very long list. A reminder that the rule book we've written for the cosmos is always a draft, never a final copy, and that the most exciting moments in science aren't when a theory is confirmed, but when it quietly breaks. Maybe the universe didn't cheat. Maybe we just didn't understand the rules as well as we thought we did. And somewhere out there, at the very edge of what we can see, in light that has been traveling toward us since almost the beginning of time, there might be an even bigger, even earlier black hole, quietly waiting to break the rules again.